Okay, so we're going to look at angular momentum and torque as vectors today. So we're going to kind of go back and forth between momentum and torque, but they work very similarly. So angular momentum we know is a vector. It has magnitude and direction. We know that means vector. So just to remind ourselves, look back over your notes, what was that formula we learned on Friday for angular momentum? Just regular, an actual rotating object. This was L is what that stands for now, angular momentum. This is the rotational inertia times its angular velocity. Again, normal momentum is mass times velocity. So when we're talking about a rotating object, instead of mass, we talk about inertia. Instead of velocity, we're talking angular velocity. Now, this is a vector because even though inertia does not have a direction, right? Inertia is just a measure of its mass and how far away we have from the center of rotation. But velocity does have a constantly changing direction, right? As we're rotating, technically I'm traveling this direction at this point. And then as I'm up here, now I'm traveling this direction. And then over here, now I'm traveling down, right? So as we rotate, our velocity is constantly changing direction. So how do we say which way these things actually point if they are constantly changing direction? So what we do is we kind of establish a rule called the right-hand rule. Basically states that angular momentum and velocity and torque, which we're going to say later, points along the axis of rotation, and we call that the z-axis. So if you have not learned that yet, we know that we have the x and y axis for two-dimensional objects. When we're talking about three-dimensional objects, we have to look at the z-axis. So the z-axis, if you can imagine like a box, or again, something three-dimensional like my calculator, we could say that this length is the x-axis, this height here is the y-axis, and then coming backwards gives us that z-axis. That gives us that third dimension. So what they call the right-hand rule helps us figure out which direction the vector is going to point. Now, again, we're going to talk about this later. It's a little confusing because this is how we say, oh, this vector points this direction. Normally, when we have linear motion, it points in the direction of the motion, and that's easy enough to figure out. We're like, well, I'm going that way, so the vector points that way. But here, what we do, we have this rotating object. What you do is you take your right hand. It has to be your right hand. You're going to curl your fingers in the direction of the motion while kind of keeping your thumb up. And your thumb is the direction of the momentum, velocity, and torque vector. So if we were rotating the other direction, what you would do is you would flip your hand upside down, because if I rotate, again, rotating this way versus I can't bend my fingers backwards, right? I can't bend my fingers that direction. So in order to get my fingers rotating the opposite way, and again, this direction versus backwards, what you do is you just flip your hand. So again, this would be pointing up versus pointing down. So now my finger is pointing down, and that's the direction of the vector. So if we have an object change directions, that vector would go from pointing up to pointing down. Now, I know this is kind of confusing. Just to clarify once again that we use this same convention, velocity and torque, because they're constantly changing. We do this to make it simple. It's not, the direction of these vectors is not the direction of the rotational motion, which is why it's a bit confusing. But it makes things simpler for doing the math later, because again, the velocity is constantly changing. So the torque and the momentum would constantly change as well, and that's confusing. So we kind of assign this to be the direction. So if you have a question, because sometimes on an AP test, they do have questions that just say, what's the direction of this vector? And if it's talking about torque, angular momentum, or angular velocity, it points out from the center of rotation. But again, it could point up or down depending on that rotation. So once more, the direction of rotation, curl your fingers. If you're like, I can't curl my fingers that way, that means you flip your hand upside down, and that would be the direction of the vector in that case. So kind of a cool angular momentum example, talking about, again, the direction of these vectors as well. We're going to look at alligator death roll. If you've never heard of these before, it's how an alligator really gets bites off of its food. It can chomp down, but if it needs to sever something, it has a hard time doing that just with its jaws because its arms can't help to keep the food still, and its jaw's not set up to grind. So what it does instead is it clamps down on the food and then rolls. It takes its momentum, again, it's rolling this way, that momentum again, then torque kind of pointing outwards to create a force that it then rips off the food. It's kind of scary looking. We're going to watch two little videos here, just kind of parts of them. One that shows a good example of the tail's use in this rotation, and then this video shows it slowed down. So let's go ahead and watch this first one here. Oh gosh, guess I should have warned you a little bit. I meant to say it's not as bad as you might think. I'm always like nature shows and watching these animals kill others. I'm like, I don't know if I can watch that, but just a little bit right there. So the important thing you want to see, we're gonna go back a little bit, try and miss the gore there, is the direction of the rotation versus his tail, and also the way his arms are kind of pulling back. You can see, so you can catch it here. So there's the rotation happening. Yep. Nope, that's that part. There we go. Okay. So watch here how his tail rotates the opposite direction of his actual rotation. And again, you can see his arms there kind of pulling back as well. His tail flips over, but his body's rotating the opposite direction overall. That's something we're going to look at in a little bit. So this one as well is a slow motion, which can help us analyze how this rotation is happening as well. Oh gosh. Okay. I was debating how long I wanted to go there. So it's kind of harder to see in this video that the tail is really driving the rotation. So let's come back. We're going to kind of analyze this and how this relates to angular momentum. So how the alligator does this, and again, it's really impressive to see through the sped up version you saw, sometimes they can get a good few spins in only a few seconds, driving their bodies over that way to get their food detached from what they're trying to eat. Yeah, it's a little scary. So there's kind of three rotations going on. There's the head kind of angles in to start with, if you kind of saw that, to get the rotation going. The body is rotating as well. The arms kind of pull back to kind of resist the rotation and kind of get it going that way as well. But then again, that tail that you saw in the first video actually goes opposite the actual rotation. He was flipping this direction, yeah, but his tail actually went the opposite way. What ends up happening here is that the total angular momentum of the alligator equals 0. We have all of these rotations happening in the body, or, in the body parts, but then the actual death roll occurs in the opposite direction. Again, really focusing on the tail to understand that. So what ends up happening here is because the angular momentum of the alligator equals 0, that's why he can have so much control over it and go so quickly. He has these kind of opposite rotations to keep himself centered, so that, again, he can go very quickly, and the total momentum actually ends up being 0. So this is going to relate to what we're going to do next, the fact that momenta and torque can be added or technically subtracted. Remember that different directions of rotations, we have to call one positive and one negative. So it's technically subtraction, but we're basically adding together positive rotations and negative rotations, gets the overall momentum or torque of a rotating object, and that will then tell us the direction of those vectors as well. So we're going to look at one example here, and then we're going to kind of come back together in class to look at some other examples. We have a seesaw. This is a very common physics problem, especially with torque, or a plank balancing is a very common example. So a seesaw is a uniform plank supported at its midpoint. Aquila and her little sister Bree sit on opposite sides of the seesaw. Aquila weighs 30 kilograms and Bree weighs 20 kilograms. And Aquila is seated 80 centimeters from the midpoint of the seesaw. So let's kind of draw this real quick. They also have the fact that with Aquila sitting on the seesaw is being tilted by an angle of 25 degrees from the horizontal. So here's our seesaw and the balancing point, we can say. Didn't draw that very well, but that's okay. Technically, the balancing point should be all the way here. This is tilted by an angle of 25 degrees right here. So Aquila is sitting, I'm going to go ahead and draw this kind of poorly, but here's Aquila. Sure. She is sitting 80 centimeters. So I'm going to go ahead and do that real quick. What is that in meters? It's going to be 0.8 meters away from the midpoint. And she weighs, again, 30 kilograms. We want to know where Bree should sit to balance this. Now, again, if you've never experienced a seesaw before, I don't know if I've actually ever been on one. I see them in the movies all the time, but we know that, again, we're talking about inertia here and talking about torque and force. When we're dealing with rotational motion, it's not just the mass, right, that can balance things out. If I have just a scale, I just need to add more mass to one side to make it balance, right? But if I have a scale this way, depending on where I put the mass over here is going to affect where I put the mass on the other side. Bree can sit farther away because even though she weighs less, if she sits farther away, she will exert a greater torque. Remember that torque is the radius times the force. So even though Bree herself can't exert that as great of a force as Aquila, she can change that distance from center and exert the same torque. So we want to figure out where Bree should sit so that the seesaw sits perfectly balanced, just flat, right? So here's what we need to realize then. If they're just balancing, what's happening here is the net torque would be what? If they're not going up or down, what would be the net torque? It's actually 0. They are balancing, that means the net torque is actually going to be 0. So what we have then is the torque that Aquila exerts plus the torque that Bree exerts are going to cancel out. So we're going to say torque of Aquila plus torque of Bree is going to equal 0. Now, here's what we need to realize though. I'm going to go ahead and redraw this picture down here a little bit bigger. We have Aquila sitting right here. Again, she's 0.8 meters away, but I'll leave that off. Let's draw where her force of gravity, because that's what's causing this to tilt, right, is her force of gravity. Draw on this picture where the force of gravity would point. Well, it would point straight down. That's her force of gravity. Bree needs to sit over here, and she has her force of gravity. Now, we need, however, when we are looking at torque, what is the formula once again for torque? The radius times the force perpendicular to the object. So notice that these forces for Aquila and for Bree are not perpendicular to our lever, like they call it sometimes, right? This is not a right angle. So what we need to do is when we go ahead, we're going to plug into here. We are going to have the distance that Aquila is from the center times her force of Aquila. But again, this force needs to be perpendicular to our lever, to our seesaw, plus the distance that Bree is, and that's what we're trying to find, times her force. I'm actually going to go ahead and add here the little perpendicular sign so that we're clear. This is going to be our end goal, but we're going to need to find these forces because, again, the force of gravity right here is not perpendicular to our lever, and we need it to be. So let's go ahead and kind of draw in here the perpendicular vectors. I'm going to actually draw this. I'm going to erase this too, actually, so that we can get this out of the way. Okay, so this is again the force of gravity for Aquila. This is again the force of gravity for Bree. But what we want is perpendicular. So if you can kind of tilt your head here, draw straight down. That is now perpendicular. That's a right angle right there, yeah, to our lever. And here's our right angle. So we want this angle. That's going to help us figure out what, again, our perpendicular, which is going to be this one, our perpendicular force is. Now we know this because we've done this a long time. Whenever they give us an angle, that angle gets transported in between the y-axis and the force of gravity, right? They gave us an angle of 25. So I know these triangles are really small here, but this is an angle of 25 degrees right here. That's the angle in between our y-axis, because we're tilted, so now our y-axis is tilted, and the force of gravity. So I want you guys to take a moment. I'm going to go ahead and pull them off, but we should know how to do this. I'm going to tilt them as well. Here's the force of gravity for Aquila. This is 25. This is the force of Aquila perpendicular that I want. This is the one perpendicular right here to my lever. Then over here we have the same thing. We've got 25. We have force of gravity for Bree, but we want this one, the one perpendicular to our lever. So I'm going to go ahead and scroll up. You can take a moment if you need to pause and copy that down. We need to figure out what their force of gravity is. I'll scroll up if you did not write down their masses, because that's how we're going to find that. And then do your trig, and then we'll click continue to check. So here are their masses. Go ahead and find their forces of gravity, and then do the trig to find the perpendicular ones that we forces that we wanted. Okay, so Aquila is 30 kilograms. So that means that her force of gravity is 30 times 10. Again, that's why we use 10, is because it makes things so simple. So her force of gravity is 300 newtons. Bree's is going to be 20 times 10, mass times gravity, so 200 newtons. So the force perpendicular for Aquila should have been, however you need to do this, be very careful, guys, to not do this every single time. Only because we have the hypotenuse are we able to skip to this. The fact that you should have used cosine of 25. If we did not know the hypotenuse, you can't just be like, oh, it's 300 cosine, whatever. You have to do your setup. It ends up actually being division. If we have the hypotenuse, we can do this. So if we don't know what the hypotenuse is, again, you'll want to write your equation. It does end up being division, but still you'll want to write your equation to double check. This is also 200 cosine 25. So let's see, I'm going to plug this in the calculator. We got 300 cosine 25. We should get 271.89 newtons. So this is the force perpendicular to the lever, to the seesaw, cosine 25. And here we have 181.26. Okay, so again, what we're going to try and figure out then is if this is the force perpendicular that they are exerting, we want to find that radius, the distance that Bree is going to sit from center to balance this. So go ahead. We know that, again, Aquila is sitting 0.8 meters away. We know that, we know the forces. Be careful here. However you want to do this, it works out either way. We can either call one of these forces negative, or what will end up happening is the radius in the end will end up being negative, but it works out either way. So go ahead, plug in what we know. We know the distance again for Aquila. We know the forces. Let's solve for the radius for Bree. Okay, so let's put this up here. So I'm just going to plug my stuff in. I've got 0.8 is the distance for Aquila. Her force is 271.89. Plus, we want to figure out how far Bree needs to sit, and 181.26 is her force. 181.26 equals 0. So let's move some stuff over and simplify this. We got 0.8 times 271.89. I'm going to go ahead and write all of this again. We got 217.512. Oh my gosh, Major, be quiet. Plus the radius for Bree, 181 point, what was that again? 26, can't even read my own handwriting, equals 0. I'm going to go ahead and do this in one step just so I can finish it off. We're going to subtract the 217 over and then divide by the 181. Again, what ends up happening is we get a negative radius, and that should make sense because we're on opposite sides of the center. But we could have also called the forces negative. They're going to, again, cause this seesaw to be pulled in opposite directions. But this works out for us here. 217.512 divided by 181.26. So we should get a distance of, this is 1.2, again, we can call it negative meters. So that's how far Bree has to sit to balance the seesaw and for it to sit perfectly and cause a net torque of 0. So we're going to practice a bit more in class. I don't want to spend too much time in the Edpuzzle. We'll come back together. We'll do some more of these problems to understand how we can apply net torque and net momentum as well. We didn't really talk about that much here to these questions that we're going to be working with.